And the final piece to put on this puzzle before we move on to heuristics to use in these situations is to consider this concept of antifragility. The antifragility is basically what we talked about in the when we discussed convexity, but we'll look at it from a different perspective this time. So we know that the physical activity strengthens the body, and physical activity is a stressor on the body, and we have evolved to manage this stressor, because if we didn't, then we would probably not be very alive right now. But also in the case of coming up with ideas, we can have these red teams in organizations, which are these people who have the designated role of shooting down weak ideas and coming up with weaknesses in them. And there's also the idea of a devil's advocate, which is a role a person can take in a meeting to uh, make it legitimate that they criticize a plan. And this role can be given as an official role for for a changing person for every meeting. Shouldn't be the same for every meeting. That shouldn't be the same person for every meeting, because then people can get really annoyed with that person. But anyway, so using this trialing to test ideas is very important. We also, you might have heard about this program called Chaos Monkey, which Amazon has deployed, where they actually severe and destroy their own parts of their own system infrastructure in order to make it in a way more resilient, so that it doesn't so that damage doesn't spread everywhere if some part is broken. And these adaptive organizations, if you have this sort of learning mindset, you can actually benefit from turbulent times, because many other organizations either fail or learn the wrong lessons, such as oh, it wasn't that bad this time, so it probably won't be any more bad any other time. And so in order to flourish and be anti-fragile, you need two main conditions. So first of all, that the shock or the stressor doesn't break the system, but there are parts of the system that can sort of safely break without taking the rest of the system with them. And also, if you remember in the discussions about convexity, that the system should be prepared to seize these unforeseen opportunities that may arise. So our first heuristic that we'll discuss here is to avoid ruin. And ruin is a term that's originally from mathematics and gambling, where so it's a state where a gambler loses so much money that they are not able to gamble anymore. And so that's called the gambler's ruin. But a ruin problem is a problem where a person cannot bounce back anymore. So they are basically permanently in a disabled state compared to how they were before. And to avoid this, we need these functionally overlapping independent subsystems. So what this means is that we have several systems that are sort of doing the same thing. And this is hugely inefficient if we're working in a complicated context, because you only want one thing to do one thing, and one system to do one function, and the function that it does the best, and anything else is just waste if everything goes as planned. The problem, of course, is that everything never goes as planned, and if such a system breaks, then the whole function will stop if they are the only system performing that function. And there's the Swiss cheese. Um, I don't know. I don't remember if it was the Swiss cheese or what it was, but the cheese slices uh, represent a situation where you have many of these imperfect um, um, systems to counter threats. And even though you can get through many of the holes, at some point it will stop because there are so many of these layers. And another thing to say about this is not to put all your eggs in the same basket. So this means diversification. So you are essentially not making one huge bet, but making many small bets. But it doesn't really work if all your eggs are in different baskets, but all the baskets are on board the Titanic. So we can't sort of diversify our climate risk, for example, because we only have one planet. And so we also need this overreaction to fat-tailed ruin risks. So because we know that if the situation is fat-tailed or the distribution is fat-tailed, then the next event might be much worse than the previous events. Whereas in thin-tails, this doesn't happen as we saw. So here's an example of how if we bring to this discussion the concept of networks. So the connectedness in your system really play a role because if you have a cascading failure, so for example a pandemic or something, then if you don't have much variety, but you have a very connected system, then something that if you have only one type of potato, and that potato gets potato plague, and all your potato fields are connected in a way that it can also spread from one field to another, then you're in a very bad situation. And in pandemic management, as well as many other fields, these connections should be adaptively manageable. So in the best situation, we might have a world where we see that, okay, so this some very bad pathogen arises, or a virus mutates, or something melts from the polar caps, and there's bacterial plague, and then we could do this synchronous global lookout of borders, where we have actually made sure that the people are safe and taken care of. So we don't need to lock people in their homes, but we can drop international travel for just a bit so that we can assess the situation and see what's going on. And we can build a system like that, which doesn't really hamper the normal person's life almost at all. Just that they can't travel abroad for until the situation is resolved. But in that way, we might be able to save the civilization.